All right, welcome linear algebra fans. A video on linear combinations. So in this video, we'll define what we mean by a linear combination. We'll see some examples of linear combinations, and then we'll pose some questions surrounding linear combinations that will end up actually going back to the idea of solving a linear system. We'll see how to write down a set of solutions to a linear system in vector form, making use of this linear combination, and then we'll talk about solutions of homogeneous systems. Okay, so here's the definition. Given a bunch of vectors from the vector space Cm, these vectors are u1, u2 out to un, and given a bunch of scalars from the scalar field C, the linear combination is given by alpha 1 u1 plus alpha 2 u2 all the way out to alpha n un. Okay, so a couple of comments here. First, a linear combination from elements of C is sort of a certain recipe or a certain sequence of scalar multiplication and vector addition, right? So we can see there are a bunch of scalar multiples, and then there are a bunch of vector additions. Okay, and by closure rules, right, we know that a scalar multiple of a vector is another element of Cn, and similarly, a vector sum of elements of Cn is another element of Cn. So that tells us that a linear combination of elements of Cn is also an element of Cn. Okay, so a couple examples. Here's a linear combination. We'll go ahead and have a look at these four vectors and these four scalars. So given these four vectors, u1 to u4, and four scalars, alpha 1 to alpha 4, the linear combination alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 plus alpha 4 u4 is well defined. Okay, and the way that we do that is just by first computing these scalar multiples, right? So alpha 1 u1 is just 1 times u1. Alpha 2 u2 is just negative 4 times u2. Alpha 3 u3 is just 2 times u3, and then alpha 4 u4 is just negative 1 times u4. And then given those vectors, we can sum them, right? We know how to sum vectors too. And when you sum those vectors, you get this vector. Okay, so again, an example of something that's not terribly difficult, but possibly a little bit tedious. Okay, so here's an opportunity for you to have a look at a linear combination on your own. So check out the worksheet. Here I'm asking you to compute beta 1 u1 plus beta 2 u2 plus beta 3 u3 plus beta 4 u4. Okay, here's what you should get. What you should get is negative 22, 21, and 1, I think. Okay, some questions around linear combinations. Here's a question. Could other linear combinations produce the same vector that we just got out of, say, beta 1 u1 plus beta 2 u2 plus beta 3 u3 plus beta 4 u4? If we have a given vector, maybe we'll call that vector w, could we cook up a linear combination of our u's that produces that w? And what about if we had some arbitrary element of C4? Could we find a linear combination of the u's that produces an arbitrary vector in C4? So it turns out that we can answer all these questions and even more by having a look at a certain linear system. Okay, so in order to give you a taste of that, let's go ahead and have a look at the linear system associated with archetype B. Okay, so we know how to express this linear system as vector equality, right? We did that previously. So once we express this linear system as vector equality, we can actually take apart the left-hand side, the vector on the left-hand side, into a linear combination. Okay, so taking apart that vector on the left-hand side as a linear combination looks something like this. Okay, so the left-hand side we know we can take apart into 3 vectors, and then of course we know that x1 here acts as a scalar, so we know how to take apart that vector addition and scalar multiplication into this linear combination of vectors, right? So here's a linear combination, a scalar times a vector minus 7, 5, 1, minus 7, minus 5, 1, a scalar x2 times a vector negative 6, 5, 0, and a scalar x3 times a vector negative 12, 7, 4. Okay, so you may recognize those vectors as elements of the coefficient matrix from the linear system. And we'll see how that's important in a moment. Okay, so to answer the question, can we write a linear combination of these vectors times x1 plus a vector times x2 plus a vector times x3 and get out the vector negative 33, 24, 5? Well, we actually know the answer to this question for this system, right? We know that the solution to the linear system turns out to be, let me just write this down. That solution is negative 3 for x1, x2 is 5, and x3 is 2. Okay, so we know that the linear system is consistent. So yes, right? This vector in question is a linear combination of the other 3. And in fact, in this case, we know that the solution of the linear system is unique. So in fact, there's only one way to represent the vector negative 33, 24, 5 as a linear combination of these other vectors. Okay, so let's have a look at the same question in terms of archetype B, the linear system corresponding to archetype B. So I'll ask you on the worksheet to go ahead and kind of work through these same details, expressing this linear system as a linear combination of 3 vectors. Okay, what you should get is something like this, where the vector 1, 8, 5 can be written as a linear combination of 1, 2, 1, minus 1, 1, 1, and 2, 1, 0. Now, for this particular system, we know that the linear system is consistent. So to answer the question of whether the vector in question, 1, 8, 5, can be written as a linear combination of these other vectors, the answer is yes. Now, of course, this archetype is an example of a linear system with infinitely many solutions. Okay, so we know that there are infinitely many choices for x1, x2, and x3 that yield this vector in question 1, 8, 5 as a linear combination. Okay, so we've seen that at least in these 2 examples, these 2 archetypes, answering the question of whether a certain vector can be written as a linear combination of others is related to answering the question of whether a certain linear system is consistent. And similarly, answering the question of whether there's only one way or more than one way to write a certain vector as a linear combination of other vectors is related to the question of whether a consistent linear system has a unique solution. Okay, and it turns out that's always true. And when we say always, there's a theorem. And here's the theorem, right? Let's suppose that columns of an m by n matrix are denoted by a1 out to an. Then X is a solution of the linear system with coefficient matrix A and vector of constants B if and only if B is a linear combination of the columns of A given by those scalars in the element X. Okay, so in other words, addressing the question of whether B can be written as a linear combination of column vectors A1 to AN is exactly the same as addressing whether the linear system AB has a solution. Okay, so that's what we sort of summarize here. Solving LSAB is the same as writing B as a linear combination of the columns of A. Now, of course, that linear system may be inconsistent, in which case no such linear combination exists. It may be consistent with a unique solution, in which case only one linear combination exists. It may be consistent with infinitely many solutions, in which case many linear combinations exist. Okay, let's go ahead and switch gears a little bit and talk about the vector form of a set of solutions. So we'll use vector notation to describe sets of solutions to systems of linear systems. It turns out this is a good way to exactly express a unique solution, and this is a good way to concisely express the case of infinitely many solutions. So here's an example. This is the augmented matrix representing the linear system associated with archetype D. Okay, so we pick off the coefficients in the linear system and augment by the right hand side. We know how to solve this linear system: row reduce, row reduce, row reduce, until you arrive at a reduced row echelon form. Okay, so a few characteristics of the linear system in this case. So you'll recall that this is a system with m equals 3 equations in n equals 4 variables. Here, the reduced row echelon form shows that there are 2 pivots, and we can partition the column indices into the sets D and F that indicate the dependent and free variables, respectively. Okay, those free variables are x3 and x4, corresponding to the variables from the partition F. And the dependent variables are x1 and x2, and we can see pretty quickly that x1 is 4 minus 3x3 plus 2x4, and x2 is negative x3 plus 3x4. So if we write that solution as a vector, we see how we can write it as a linear combination. Okay, so here is that solution in vector form as a linear combination. Now, I'll point out that this system has n minus r equals to 2 free variables, and we can express the solution of that system as a linear combination of 2 vectors plus 1 more. Now, the elements of those vectors sort of come from this reduced row echelon form, right? So the minus 3 and the minus 1 come from moving the 3 and the 1 to the other side of the equation. And similarly, the 2 and the 3 come from moving the negative 2 and negative 3 over to the other side of the equation. Okay, of course, there's also an element 4, and those elements come from sort of the right-hand side here. Okay, so again, the point being that we can write the vector form of the solution as a linear combination of 2 vectors that come from those n minus r2 free variables plus 1 more. Let's have a look at another example. Here's another example, a more difficult one. If we have a look at the system of 5 linear equations in 7 variables, that's represented by this augmented matrix in reduced row echelon form, we can sort of play the same game and express the solution of the corresponding linear system in terms of those characteristics R, D, and F. Okay, so here's what that looks like. In this case, we see that there are R equals 4 pivots. The partition of column indices into the sets D and F are D equals 1, 2, 5, 6. F equals 3, 4, 7, 8. That indicates dependent variables x1, x2, x5, and x6, and free variables x3, x4, and x7. Okay, and we see that there are n minus r equals 3 free variables. So sort of what we expect based on what we saw before is to be able to express the solution of the system as a linear combination of those three vectors, perhaps plus one more. So let's see how that all pans out. Okay, so here's the vector form of the solution to this linear system. Now we sort of again expect this to be able to be taken apart into a linear combination of three vectors corresponding to those three free variables plus one more. And we can see where the elements of those three vectors plus the one more comes from if we take apart those variables carefully. So first we have to make sure that we get x3, x4, and x7 in their correct spots. Okay, so in order to do that, we'll fill in some ones and zeros to make sure that in those particular vector elements we get x3, x4, and x7. And then we can work down our vectors to ensure that we get the right vectors corresponding to those free variables in our dependent variables also. So the correct dependent variables corresponding to our x3 free variable come from here. The correct dependent variables corresponding to our x4 free variable come from here. And the correct free variables corresponding to our x7 free variable come from here. Okay, and finally, we see that we can fill in this one more vector with what we get out of the row-reduced echelon form corresponding to that vector of constants. Okay, and again, those numbers come from that vector of constants, ensuring again that we get x3, x4, and x7 for our free variables as desired. Okay, so for a consistent linear system, you can always play this game. Always means there's a theorem. The theorem is sort of indexy, but here it is. Theorem says that if AB is the augmented matrix for a consistent linear system, and B is the reduced row echelon form, and we take the vectors C sub I, C and U sub J to be corresponding to that row reduced echelon form, then the set of solutions can be represented by a linear combination of n minus r vectors that correspond to the free variables, possibly plus one more. Okay, and you can see sort of the same form that we had before, where we have some negatives and some ones and zeros to ensure that we get the correct numbers for the free independent variables on those solutions. And then you can see that the vector of constants is given by zeros or the element from B in the row reduced echelon form. And again, these sets F and D are the partition of column indices, respectively. Okay, so this is, again, a step toward making our process of solving a linear system of equations methodical, right? We can see how to put each solution into a vector form. Okay, so I'll go ahead and illustrate this theorem on the row reduced echelon form corresponding to archetype I. So archetype I is a linear system of m equals 4 equations in n equals 7 variables. Okay, we can see that there are r equals 3 pivots, so we expect there to be r equals 3 dependent variables, and we expect there to be n minus r equals 4 free variables. Okay, so in this case, we would expect to be able to express the solution of the linear system as a linear combination of 4 vectors plus one more. Okay, so the first thing we'll do is sort of form those 4 vectors where those 4 vectors correspond to our free variables, x2, x5, x6, and x7. Okay, so filling in our 4 vectors plus one more with ones and zeros to ensure equality for the free variables looks something like this. Okay, in absence of everything else, we want to ensure that x2 is represented by x2, x5 is represented by x5, x6 is represented by x6, and x7 is represented by x7. Okay, so now we can fill in these dependent variables. And again, the elements in the dependent variables come from the columns associated with the free variables with a minus sign, right? Because we're thinking about moving those to the other side of the equation. So, for instance, the x2 variable comes from the second column. The coefficients for x1, x3, and x4 corresponding to the free variable x5 come from the fifth column. The coefficients for x1, x3, and x4 corresponding to the free variable x6 come from the sixth column, and the coefficients for x1, x3, and x4 corresponding to the free variable x7 come from the seventh column. Okay, and finally we can fill in the vector of constants. Okay, cool. So there is our vector form of the solution of this linear system, again expressed as a linear combination of n minus r, which in this case equals 4 vectors plus one more. Okay, let's do another one. Here's another one. The linear system corresponding to archetype L. Archetype L ends up being a homogeneous linear system. There are m equals 5 equations, n equals 5 variables. Here is the augmented matrix in reduced row echelon form. We've gone ahead and added the vector of zeros here. So we can sort of proceed similarly. We expect to be able to write the solution as a linear combination of n minus r equals 2 vectors plus one more. Okay, so here are those 2 vectors, right? We see that the free variables are x4 and x5, so we'll fill in ones and zeros to ensure equality for those free variables. Okay, here's equality for those free variables. Then we can go ahead and fill in the dependent variables. Again, the coefficients for x1 and x2 and x3 corresponding to the free variable x4 are going to come from that fourth column, and the coefficients for x1, x2, and x3 corresponding to the free variable x5 are going to come from the fifth column. Okay, so here are those variables. And then finally, we can fill in the elements of that extra vector of constants corresponding to this augmented portion. Okay, so as expected, the solution, the vector form of the solution of this linear system can be expressed as a linear combination of 2 vectors plus one more. Now here, with this homogeneous system, it turns out that that vector of constants is 0, right? And that makes sense when we have a look at it in hindsight, because of course the augmented column will be 0 because of a homogeneous linear system, and that one more vector corresponds to that augmented column. Okay, so it turns out that for a homogeneous system of equations, the set of solutions can always be described in terms of a linear combination of n minus r vectors. Okay, this is really important, and we'll sort of come back to this a little bit later, that we can always express the solution of a homogeneous linear system as a linear combination of n minus r vectors. Okay, so we'll wrap up this section talking quickly about particular and homogeneous solutions. Okay, so here's the theorem, and I'll just direct you to the text. If W is a solution of a linear system of equations, then y is a solution to a linear system of equations if and only if y is equal to that solution w plus some other vector z that's in the null space of the matrix A. Okay, so here again we call y and w a particular solution, and z is a solution to the homogeneous system of equations, right? Because elements of the null space correspond to the homogeneous solution. Okay, so I'll sort of pose a question here that will lead us to a discussion in our next section. And that question is, what about square matrices? We know that in the case when A is non-singular, the linear system has a unique solution. Okay, well, when A is singular, things are a little bit different, right? And there's a null space, so we'll see then for square matrices how to summarize this theorem about particular and homogeneous solutions. Okay, folks, that's it for this section. A lot of information here on how to concisely express the solution of a consistent linear system as a linear combination of n minus r vectors plus one more. And a big theme here is that in the case of a homogeneous linear system, that one more vector is a zero vector, so we can express the solution of a homogeneous linear system as a linear combination of n minus r vectors. All right, have a great day, and we'll see you next time. Bye-bye.